Hi, this is HUST-China 2016. We are a young and energetic team consisting of 17 undergraduate students. Inspired by William and Mary 2015 finalists, we decided to do something for iGEM this year. Considering that gene expression regulation is an important part of synthetic biology, we made a survey to figure out what kind of gene expression problems that most teams are faced with. We found that there are a lot to do. According to our survey, 75% of respondents have ever considered to utilize a stable state to optimize their project. However, they thought designing a multi-stable circuit is difficult. If we can relieve iGEMers from constructing complex circuits, more and more people will easily begin their own project. The result of our survey also shows that lack of robustness is the problem that most of them encounter. Therefore, we are trying to enable our toolkit to filter the input signal to guarantee stable gene product expression. 1/3 of respondents have mentioned that they could not find a promoter that had just suitable identity. Since seeking for substitution is not always the best solution, here comes our signal filter's second feature, setting threshold by adjusting regulatory promoters and the amount of its interactive protein. All in all, we provide a fundamental gene expression toolkit. Just like a vending machine, users can divide input and the related output by themselves. In order to correspond to different modes of input and output, we provide two versions: tree-stable and bistable expression formats. Tree-stable circuit is redesigned from bacterial phage lambda. Different combinations of input signal can lead to different results. When pose 1 occurs, we can get our first output, gene of interest 1 stable state. When pose 2 occurs, the stable state of output 1 will soon be interrupted. Gene of interest 2 will show up gradually and reach a stable state. When there is no signal, both genes of interest will be expressed. In conclusion, this toolkit can switch to 3 stable states. Bistable expression kit is designed based on ABA response pathway. When on signal comes up, gene of interest will reach on state. When users want to turn off gene of interest, a post off signal will make sense and gene expression will be shut off. Now you might ask how to use it. Here we go. We considerately provide an example of application: therapy of lactose intolerance. Lactose intolerance refers to the inability to digest lactose. Due to lactase deficiency, unabsorbed lactose can be fermented by bacteria in colon, which leads to the production of some gases and short-chain fatty acids. This fermentation products, especially the acid, and cause various abdominal symptoms. We provide a new aspect for the treatment of lactose intolerance based on the concept of fecal microbiota transplantation. Our strain will be transplanted to the intestine to deal with surplus lactose. Well, this is an application of prokaryotic version of signal filter. We set gene of interest 1 as ILDH and gene of interest 2 as beta-galactosidase. When body intakes large amounts of lactose, lactose-sensitive promoter PLAC together with PRE will trigger a certain quantity of C2 and CRO to be expressed. C2 will serve as a transcriptional activator to initiate PRE to form a positive feedback loop. CRO expression will soon reach its stable state to inhibit PRM. Therefore, we can get our first output, ILDH stable state. ILDH is able to transform lactic acid into pyruvate, easing acid irritation. Considering that FTSH normally exists in our host strain can degrade C2 and then destroy positive feedback, we put a protector C3 to inhibit FTSH. When the pH in intestine comes back to normal, more than 7 and less than 9, pH-sensitive promoter PATP2 will drive the expression of C1. The stable state of ILDH expression will soon be interrupted by C1's expression because C1 can bind to the upstream of C3 and gene of interest 1 to block them. Without C3, FTSH will first degrade C2. Then CRO expression begins to shrink. Beta-galactosidase will show up gradually and then reach a stable state. It not only degrades lactose but also accumulates for the next lactose intake. The system has two main advantages. It realizes threshold control and enhancement of robustness and persistence. This summer, we made great efforts to characterize our toolkit. Days were busy and we had fun. Looking forward to your participation.